this, and it is officially recording. Hello all, welcome, welcome, welcome. It's great to see so many of you jump in straight away. It's brilliant, so many familiar faces, well, not faces, but names. Excellent to see you on this fine, snowy, cold Monday. Brilliant stuff. So just as everyone's joining and coming in, I'm just going to share my screen so you can see my slides. And we're going to begin the webinar. So first of all, to any of you who have seen the work in your classrooms already and are a bit confused, please don't worry. What I'm going to do today is I'm going to, first of all, spend a little bit of time going through exactly what I want from you today. Now, or this week, I should say, if you have any questions, just remember that it is myself, but also Mrs. Bush is in webinar as well. Now, this week, we have kind of given it the tagline, reflect, review, revise. And we're trying to build upon what you guys said to us in the Google form that we sent to you all about, what do you want from your online learning experience? And one of those things was that you'd like more time to work on things. You'd like time to go back and improve upon work that you've been given feedback on. And at the moment, and as of our previous weeks, there kind of wasn't that time built into the timetable to do that. So us as a department, and I know other departments are doing the same, have decided that this week we will be looking at work we've done previously, looking at how to improve that, and then looking at how to really nail down those topics so we feel really confident going into half term. So today's revision webinar is a revision webinar, and I'm going to take you through all the things that I've covered with you in C2 so far. The slides are similar to the ones that you've seen before, but they aren't the exact same. There are differences, and hopefully they're a little bit more tidy in that they're just to revise from. So there's less information, but it's more key information. Then your work for this week, it seems a little bit like there's loads, but let me clear it up for you. So the first thing that you have is a self-assessment form that will be put into your Google Classroom. Now, this is a Google quiz, but it's not a quiz based on how much you know. It's a quiz where you're literally going to go through and say how confident you are with different topics. And the reason you're going to do that is because as your teachers, we can look at which topics most of you feel confident with and which topics most of you need more help with. And that information is going to be used by us in some individual class Zooms that we're going to be setting up this week. So most of your teachers will be contacting you in the next week to set up some Zooms that you can do as a class, because it's much easier for us to give you really good feedback based as a class and only you as your class. So my class, I have already sent you an email and popped something in the Google Classroom, and I know that other teachers have done the same. And in those Zooms, we'll be able to go through stuff more specifically and more tailored to you as a group. And that way you can ask questions of your teachers and get direct answers as well. What you're going to do after that, or at the same time as that, is you're going to be going back through the tasks that you have submitted in the last few weeks. And you're going to be looking at the feedback you have received. You're going to be looking at that feedback and improving on the questions. And I'm going to show you what that looks like in a second. The reason we do this is because feedback should be there to help you improve. It isn't there just for you to read and go, all right, brilliant, and then move on. The whole point of it is so that the next time you do it better. And we're trying to give you that opportunity this week. And then if you are somebody who is super up to date, so all of your work has been submitted, you've got nothing to catch up on, you've responded to your feedback, you didn't have much to respond to and resubmit to your teachers, well, then there is a sheet that you will have uploaded with what's next tasks on them. And I'll show you that now. So what I'm going to do is I'm just going to exit here, and I'm going to show you the self-assessment quiz. So this quiz, as you can see, has statements that come directly from the specification, and the specification is what tells us as teachers the points that you need to be taught, so the stuff that could come up in the exam. So what we've done is we've taken out the key bits from the specification that we've gone over so far, and you're going to decide whether you're okay with it, you feel confident with it, You could revise this again yourself, so you might need to go back over it yourself. You've kind of got the concept, but there are some gaps there. You're not totally confident. Or I would like to go over this again in a webinar. And your teachers will be able to use that data, that information. It will come through like a little pie chart for us over here, and we'll be able to design our specific webinars based on that. This will also help you when it comes to revising, because if you said to yourself, I could revise that again, well, then that's what we need to do this week as well when we get a chance. Now, the tasks to do after you have completed and improved upon your work will be found on a document that looks like this. And this document is there, like I said, as a bit of an extension. Now, your teachers and I, we want to see you submitting work this week. We want to really see you pushing yourselves to improve. And this is one way you can do that after you've resubmitted your tasks. Now, the first thing here is about revision. And I've included a video here that I recorded for year 11. And this video takes you through how to create a mind map for C2. Now, it is for the whole of C2, so you'll only need to watch the first little portion of the video, but it will explain how to revise it. I've also just finished recording a video on how to make good flashcards, and I will upload that too, so that you can create those resources. What we would like you to do as your teachers is to send us a photo of what you've done, just so that we can give you some feedback and to see how much you're getting done in your time. If you do manage to finish this, and as a complete extension, there is a task here that's going to see you being prepared for the work we can do after half term, which is on a principle called Le Chatelier's principle. And there are some videos and some information for you to make some notes on. But again, that bottom bit really is an extension, and it'd be really good to see you getting onto it, but there isn't that pressure to. Now, when we talk about reviewing, reflecting, and revising, we're talking mainly about looking at the work you've done in your classroom and responding to that. So on the board is some feedback that I've given, and I haven't included any of my classes' names or their actual work, but I've just shown you how I would give feedback, just so you can see what we're talking about. So the reflect process, you're going to go back into your past assignments on Google Classroom. So they've been returned to you. You may have a mark on there. You may have some feedback in a little box just next to the mark that explains to you sort of the good and the points to improve on in your task. You may have an edited document where your teacher has added annotations about specific questions. You may have a voice note called a mote that we've been using. I know Mrs. Bush uses them lots, that we use to give you verbal feedback on your work as well. So you may have feedback in any of these ways. The first thing is you need to read that really carefully. The next thing is to improve your work. So, for example, I here have written on a question that was left blank, a summary of the question itself. So I've improved the question in terms of making it easier to understand. I should see you resubmitting your work with that question answered. And you can do that. You can open the work you've already submitted and then press hand in again. And we, as your teachers, will correct that and make sure that you've done that. That is the review portion. And once you've done that on your tasks, then you will need to go and revise the additional stuff that you need to consolidate. So based on the quiz that you've done, based on the feedback you've been given, what bits of this module do you need to go back and look at? Now, we have done quite a lot in this module already. In fact, when I wrote this out earlier, and I was thinking, we've only done 2 webinars of C2. And then I looked at all of the things we've covered. I was like, wow, that's pretty damn impressive. But actually, we know, don't we, that lots of this all comes together. Now, this webinar is going to be a revision webinar. So it's going to be quick. And at the end of the webinar, I have added additional links and additional resources that you can click on to go and look a bit more in detail at specific areas. Now, the aim for this today is I want to go through the revision material, but I would like there to be some time at the end for questions. But remember also that this week, your teachers are going to be arranging for you to have smaller group Zooms. So if you do have questions, have a go at some of the work, and then you can keep those questions for when you're going to go and meet with your teachers. Okay, so that's the idea for this week. Now, those topics that I've written on the slides there, those can be used to structure your revision. And I've popped them on there. We're not going to go through everything on here in lots of detail, but these are the things we've specifically gone through. Now, I want to see how much you remember. So I have got a poll for you, and it's got 6 questions, which I know doesn't feel like a poll, probably feels a bit more like a test. But the reason I'm going to do this is so that I can see what bits of this slideshow I should spend more time on. And also you get a bit of an indication as to what you know already. Now, before I put the poll up, please read all of the options before you select one. I have done this many, many times now with many different webinars, and people tend to click and they go, oh no, that wasn't what I meant at all. So I'm going to launch the poll now, which is poll 3. And I'm going to be seeing live how you do. So reading through each of the options before you click one even. And they are quite similar. I've done it on purpose. I'm going to give you quite a few minutes on this. I'll say quite a few, 3 or 4. The first one, what is an exothermic reaction? Second one, if I was measuring 50 milliliters of hydrochloric acid to react with magnesium ribbon, what would be the appropriate piece of equipment to do that? What could you use to measure the amount of hydrogen produced in a reaction? Click any that apply. Why does increasing pressure increase rates of reaction? What is concentration? Describe the difference between the curves of a reaction at a higher rate and that at a lower rate. Remember, a higher rate is one that's happening more quickly. What does that symbol mean? I can't say what that symbol is because then I give away the answer. And lastly, what does a catalyst do? So I've got one of you has voted. Oh, no, 2. I really want to see you have a go at these questions, but I know there's quite a few, so it's going to take you a few minutes to have a little look through. Okay, quite a lot of differences in answers, which is interesting for me at least. Good. Good, I'm starting to get your results in nice and quickly now. Now remember, these are totally anonymous, so please don't be afraid to put an answer in. I don't know who said what. It's just to give me an idea of how much you know so far. Remember, I teach quite a few of you, but there's a lot of you I don't teach. So it would be really, really useful to get a really broad understanding. So about half of you have submitted some ideas. I'm looking for quite a few more of you to have a go. You've had 2.5 minutes. I'm going to give you about 1.5 minutes more. Okay, we're doing very well. Good answers. Okay, you've got about 30 seconds. So if you are stewing on an idea, just get something in so that I can see what we're thinking. Okay, this is really useful for me, Year 10. It means that I know exactly what to focus on more in the next 30 minutes or so. So 20 seconds more. If you are erring about an answer, just submit something so that I can see, and then we'll move on. Okay, so I'm going to end the polling there, and I'm just going to share some results. And remember, the orange one shows us the most popular answer. Okay, it doesn't show us the correct answer. I'm going to tell you the correct answer. So what is an exothermic reaction? Well, the correct answer is, in fact, the most popular one here. A reaction where temperature rises due to energy being released to the surroundings. So the second most popular answer talked about energy being released to the surroundings, but got the temperature change incorrect. So temperature increases because more energy is around the particles now, which causes the temperature to rise. Okay, that energy is released as heat. Well done. Okay, this one was done very, very well. So if a measuring cylinder, sorry, if I was measuring 50 milliliters, I would use a measuring cylinder. Okay, a pipette is really, really accurate and precise, but only when measuring very small amounts. So if this question said, how would you accurately measure 5 milliliters? A pipette is a really good example. Now you can get larger pipettes, but we don't use them in school. So for our experiments, we would use a measuring cylinder. A beaker and a conical flask normally hold the reaction components. They hold your reactants. They're not really there to measure things, okay? You give you an indication of how much you've got in there, but it's not a precise way of measuring it at all. Sorry. So question 3, what could you use to measure the amount of hydrogen produced in a reaction? Well, this one was I was a bit cruel here because 3 of these are actually correct. The one that's not correct is the one that you would normally weigh things with. So weighing scales wouldn't be appropriate here because hydrogen is a gas. And I haven't told you hydrogen was gas, but that's kind of the trick here. A gas syringe is probably the most accurate way of measuring it. And I've showed you pictures of those before, and I'll show you another one today. An upturned measuring cylinder is something that some of you will have done in class. I know my class definitely have, and it's actually a required practical. And Ms. Yarvi made some amazing videos about rates of reaction practicals that are on the Science YouTube channel. So I would really advise looking at that as part of your review process for this week. You actually can use a balloon. Okay, you can use a balloon to capture any gas made, and then you can work out how much gas is within there by either extracting it into a gas syringe, or you could, if it was a dense gas, you could weigh the difference before and after it being inflated, or you could measure the volume of the balloon and see how much it had stretched. It's quite a complicated way of doing it, but it is a way you can do it. Why does increasing pressure increase the rate of a reaction? Brilliant that you all got this. Well, nearly all, but most of you. Particles are closer together. Now, when it says more particles, there aren't any more particles when you increase the pressure. There is more per unit volume, as in if you were to look at the volume and how many particles there were per each unit of volume, there would appear to be more, but you're not adding anything extra there. You're just making the container smaller. And that means everything gets closer together. Leading on from that, concentration is the mass or number of particles per unit volume. That phrase, per unit volume, is really going to help you because sometimes it can be hard to put that into words, per volume or in a certain volume. In a certain volume is fine, but per unit volume just makes your answer a little bit more scientific. Describe the difference between the curves of a reaction at a higher rate or a lower rate. You're absolutely right. If it's got a higher rate of reaction, you're going to get a steeper line. And that's because it's going to get to its total yield before the lower rate. They still meet at the same point. That's really important. We'll talk about that in a second. And last couple of questions. What does this symbol mean? It is a reversible reaction. You can see here that I lost my energy for writing options because the number of options per question is significantly reduced. But that is a reversible reaction when you see those two half arrowheads. And what does a catalyst do? It increases the rate of a reaction by lowering the activation energy. It does not give the particles more energy. It just allows particles at lower energy to still result in successful collisions. Okay, so they're quite complicated the way they work. But if you can remember that it lowers activation energy, you are set. So let's go through some of these things together then. Now, like I've said, I will be going through things, but this is revision. So you don't get the same level of detail you did the first time. But this should help you to highlight those areas in which you need to go away and look at in more detail. So, in general, what is collision theory? Well, collision theory is the idea that in order to react, particles need to collide and collide with enough energy that it results in a reaction. And that minimum required energy to start a reaction is known as our activation energy. And you can see that down here on the graph, the activation energy is your bump, okay? It's the little bump between the reactants and the products. Now, let's see how much we can remember, ladies and gentlemen. Is that graph down the bottom showing me an exothermic or an endothermic reaction? Stick your answers in the Q&A for me. You can do it anonymously. Is that graph showing me an exo or an endothermic reaction? Apologies. Good, good. Okay, a real mix of answers there, but that's okay because we're going to go through it. So this is an exothermic reaction, okay? And it's an exothermic reaction because the reactants are at a higher energy level than the products, and all of that energy here that is excess has been released as heat, okay? So that's how we know it's exothermic. We're going to review it in a second in the revision slides, so don't worry too much. So collision theory, that is the basic idea that things need to bump into each other with enough energy in order to react. That definition at the top is a really solid definition that you might want to put on a flashcard when you review this to come back to revise it. Now, what we normally talk about, and I'm going to move my face here, what we normally talk about when we talk about collision theory is how can I use that knowledge of collision theory to increase the rate of a reaction. Now, if I had my own chemistry company, I don't, I'd be quite rich actually if I did. I'm not. If I had my own chemistry company and I made something, so I might make catalysts, I might make catalysts for different industrial processes. And I might be wanting to make those things as fast as possible, because when I make them more quickly, I spend less money on storing, on conditions, on labor. I spend less money on all of those things, and I make more product per day. So increasing the rate of reaction is really important to know. And in order to increase the rate of reaction, I can do one of three things. I can increase frequency of collisions. Now that just means I can make things collide more, but increase frequency of collisions, that's the way the examiners like you to say it. I know because I've seen a number of mark schemes preparing you guys in the last couple of weeks. So increasing frequency of collisions. The second thing you can do is make those particles have more energy in the first place. And the only way we can do that in the things that we're going to go through together is by increasing temperature. And the third thing you can do is both. Okay, and again, we're really only talking about temperature there when we're talking about doing both. So increasing frequency of collisions or increasing the energy the particles have so that you've got more of them at the activation energy, or doing both. Now, in this grid, and bear with me because I know it's not very user-friendly on a presentation, but I was thinking about when you go back and use these to create revision resources. But this grid, this table, has got everything I've taught you about these 5 variables, about the 5 ways that you can change the rate of a reaction. And I've given you in that theory column the exact way you should be aiming to answer a question on it. And I'm going to read through them really quickly with you. And I want you to really appreciate how similar all of these definitions are. Because in every single one of them, you're going to mention rate of reaction. And in every single one of them, you're going to mention collisions. There'll be something different for each one because you're talking about different things. But those 2 things must be said. For each of them, I've given you a diagram. Now, I also appreciate that it might be difficult for you to see these diagrams depending on what device you're using at the moment. Again, what I was thinking of is when you make your flashcards or mind maps, these might be nice diagrams to make a note of on there. So you can, when you have the slide, you can look at them a little bit more closely. So temperature. Let's look at why temperature increases the rate of a reaction. So increasing temperature increases the frequency of collisions and makes those collisions more energetic. Remember, more energetic means each particle has more energy. And in the case of particles, when they've got more energy, they're going to move around more. This, therefore, increases the rate of reaction. That doesn't make sense there, but you know what I mean. Now, surface area to volume ratio. I've got a diagram here. Remember, the first thing to remember with surface area to volume ratio is that the smaller the pieces, if you cut them up really small, if it's a powder, the larger the surface area. That can feel a little counterintuitive, but remember, the smaller the pieces, the more particles available to react at any one time. Think about it in terms of sugar. If you pop a sugar cube into your tea, you go to a cafe where they have, they don't really do that anymore, but if you had sugar lumps or sugar cubes, it takes a while for that to dissolve. And that's because the outside of the sugar cube's got to dissolve first, then the next layer is exposed and can dissolve. Whereas if I've got powdered sugar or granulated sugar and I put a spoonful in my tea, that's going to dissolve nice and quickly. And that's because more of the sugar is actually available to react with the hot water straight away. So let's think about specific theory. Increasing surface area to volume ratio increases the number of particles available to react at any time. This increases the frequency of collisions and rate of reaction increases. Now, in questions about surface area, they often want you to be able to identify what things have a larger surface area. Smaller particles will have a larger surface area. So powders will have a larger surface area than chips, for example, of marble. But they also will sometimes give you the structure of a solid, and they'll say, which one of these has a larger surface area? And what you need to be looking for is the one that has like dips, or the one that has areas that move in and out, or has holes in the middle, because that all increases the surface area as well. Pressure. There's a little diagram to show you what I mean by low pressure and high pressure. If there's less space between the particles, they're closer together. That means there's a higher frequency of collisions and the rate of reaction increases. Concentration, very, very similar. Sorry, there will be more particles in a given volume, or, as I said earlier, per unit volume. This means particles will collide more frequently. This means that your successful collisions increases and your rate of reaction increases. That successful collision bit isn't essential in your answer, but it's there because it can make the answer flow a bit better. And lastly, a catalyst. That graph down there is really important because it explains how a catalyst actually works. So catalysts increase the rate of a reaction by providing an alternative pathway with a lower activation energy. And so on that diagram, you can see that red line and that blue line. So the blue one is the activation energy without a catalyst. That activation energy is nice and high, or high, not nice and high. And the red line shows without a catalyst, and that's lower. So it's easier to get over that bump, isn't it? Okay, and so that's why it's easier for things to react when they have a catalyst and they react more quickly. So that is collision theory and how to increase a rate of reaction. This is something that you can use for flashcarding. And again, I've made a video, I'll upload it as soon as we're finished here, that will help you understand how to make flashcards. And these are the really perfect definitions to pop on the back. Now, knowing how to increase a rate of reaction is one thing, but how do I actually investigate it? Well, on the screen, I've got lots of images here that we're going to talk through quite quickly. So I've given you lots of questions in the last 2 weeks about these two equations here. How to work out the rate of reaction. And it's always quantity of reactant used over time taken, or quantity of product made over time taken. So what does that mean? If I start with something solid and I slowly have a look and see how long it takes for it to disappear, that's looking at how quickly it took for that reactant to be used up. If I'm looking at a product being formed, I'm either measuring gas coming off, or I'm looking at how quickly a precipitate forms. And that can show me how quick my reaction is going too. Now, here are different practical methods to do that. So this first one here is measuring a gas. You will see that you've got an upturned measuring cylinder and the reaction happens in here and the gas is bubbled through to the measuring cylinder, and you can measure how much gas is being produced per minute, if you like, in there. Almost the exact same reaction with slightly different equipment here. You've got a gas syringe, the gas pushes the plunger out, and you can measure exactly how much gas is being made per minute or within 5 minutes, etc. Now, this one here is a precipitation reaction. And in the exam, if you're looking at this type of reaction, they're going to mention a reagent called sodium thiosulfate, because it's this reaction here. You don't need to know what sodium thiosulfate is, and you may well have done this reaction in lesson. It's the one with the black cross underneath it, okay? It's the one that's most easy to recognize in an exam. So you start off with a clear solution, you add your second reactant, and it starts to go cloudy. And what you do is you record how long it takes for it to go so cloudy that you can't see the cross anymore. And you could do this with different concentrations. So you could start with 1 molar or 0.1 molar and go up and see how long it takes to go cloudy. And that's a really nice experiment. But obviously it requires on you deciding when you can no longer see the cross. So it's not as precise as other experiments. This one in the bottom left is a really lovely experiment to do where you're simply weighing how much reactant you've got left. So we're doing this first bit here. So you're measuring your dilute hydrochloric acid is reacting with your marble chips. You're seeing how much the mass decreases as you go on. Now, in any experiment where mass appears to be lost, because remember, you can never create or destroy things, you just lose it to the atmosphere if it's a gas. So any time that the mass appears to decrease, then you know you are making a gas. Same with if it bubbles, for example. Now, one thing that I want to go over with you, year 10, and this is based on my class, but I know it's true of other classes too. That bit of cotton wool in the conical flask does not stop the gas. Cotton wool is not a good enough seal to stop the gas leaving. And lots of you, when the question was asked about why do we put cotton wool in the top of the conical flask, said to stop the gas escaping. We don't want to do that, okay? There's no need for us to do that. We don't mind losing the gas because it helps us investigate the reaction. The reason we put the cotton wool there is to stop the acid spraying. Sometimes, and those of you who are in my class will remember, sometimes this reaction can be a little bit vigorous. And sometimes it may, when you add the marble chips to the hydrochloric acid, sometimes it bubbles up and fizzes quite vigorously. And that might mean that the acid kind of spits out the top. You don't want that to happen because that will make it look like you've produced loads of gas, but you haven't. You've just lost a load of acid. So the cotton wool is there to stop any spray coming from your solution. Now, those are just some different examples of how to do it. Now, like I said, if you go to the Science YouTube channel, there is a couple of videos made by Miss Yarvi, and they are brilliant, and they go through these practicals in more detail. Now, when you've done that practical, you'll be able to plot a graph. Whatever practical you're doing, you'll be able to plot a graph where you'll be able to compare how quick the rates of reaction are. Now, what you were great at in the poll is being able to explain to me that the faster rates of reaction have a steeper line. You're absolutely right. In exams, they often say, use data to explain why this one, or how you know this one is faster than this one, or how the graph shows this one is faster than this one. And you can work out the gradient and say, well, this gradient is this, which means that it's steeper and therefore it's the faster rate. But another easy way to do that is looking at the endpoints. So both of these graphs, and it's really important that they do this, start at 0 because it's about how much product is being made and you've made no product at the beginning of a reaction. And they get to the exact same spot because they're going to end up making a total amount, the same total amount. If you leave them for long enough, they'll both get to the same place. But it takes less time to get there for the faster reaction. So if you wanted to prove that this reaction happened more quickly than this one, ignoring the fact that the line is steeper, you could look at how long it took for the line to get to its maximum yield or to the top amount of product that's being made. That is a really easy way of showing that this one's faster. So imagine this is 30. I don't know. I don't have an axes label here. For this one, it might have taken 5 minutes to get to 30 centimeters cubed of gas. This one, it might have taken 15 minutes. And that shows that the pink line is your faster rate of a reaction. So the reason I'm going through that is because that's a really common exam question. When I was going through exam questions to give to you over the last couple of weeks, there were fewer 6 markers in this topic, but lots and lots of graph questions. And I know people get a bit worried about graph questions, but honestly, if you just look at what the graph is showing you, you can get lots of marks with very little work or very little prior knowledge. The difficult bits about graphs are the difference between these two things here. Now, in your exam, you may be asked how to work out the rate of a reaction from a graph. And they'll give you a graph and you'll have to use it to work it out. Now, there are 2 ways they could ask this question, and one of them is slightly easier than the other. So on the left-hand side here, you can see that the question asks you to calculate the mean rate of reaction after 20 seconds. So if it asks you for the mean rate of reaction after 20 seconds, all you do is go up from 20 up to the line, measure across, and then do the total amount of product made over time to get your answer. Okay, just like the equation that we saw earlier. However, if the question says, what is the rate of reaction at 20 seconds? Here, we're not asking you to say, well, what is the rate of reaction after all of this time? We're asking, in this specific point, how fast is the reaction going? And when you do that, you have to draw a tangent. Now, sometimes all they'll want you to say from the exam is that you know that you need to draw a tangent to measure gradient of the line here. Sometimes you have to actually do it. And this is a higher only piece of content, and it is tougher. Now, there are questions on your previous work where you've been asked similar questions about that. And in the previous slides that we did on this, in the week beginning the 25th of January, we actually went over this in more detail. But I really wanted to draw your attention to the fact that if it says mean rate, it's the really easy way of reading from the lines. But if it says at a certain time, not after, at a certain time, then you will need to draw a tangent. Okay, math skills are really important in science. All right, they're about 30% of your marks in your exams, and they're never particularly hard. Okay, it's just practice, and we will do lots of graph practice as we continue going through chemistry. Now, energy changes. This is something that threw quite a few people last time, and it is something that you did in C1, but I wasn't here when you did C1, and it might have been one of those topics that coincided with the first lockdown. So it might be something that you can't remember as well, or that you didn't do in as much detail. So don't worry, it's here for you, and it's quite simple once you get your head around it. The first thing you need to remember is that if it gets hotter, it's exothermic. If it cools down, it's endothermic. Hence why it's red and blue in the on the slides. We are going to continue with C2, by the way, after half term. This is just a stopgap to think about what we've done so far. Now, on the screen, and I apologise, those aren't very nice to look at, but I've just made them big so that we can all see them. On the left-hand side, you've got an endothermic reaction. And on the right-hand side, you've got an exothermic reaction. Now, we know that endothermic reactions, the temperature decreases. And it decreases because in order for the reactants to make the products, it needs to absorb energy. And where does it get that energy from? Well, it gets the energy from this space around it, the heat energy from the surroundings. So as that heat energy is absorbed into the bonds of your products, because remember, we're making your products, that energy comes from the surroundings and therefore temperature decreases. So it gets colder because you're absorbing energy. Exothermic, actually, energy is released because the products don't require as much energy in their bonds than the reactants already have in their bonds. So when the reactant bonds break and then they make the new products, there's all this excess energy left over. And that energy gets released. And it gets released in the form of heat. So with your thermometer in your reaction, you're going to see a temperature rise. Now, like I said in the last webinar, if you can remember it one way, you can remember it the other way. It's the exact opposite, okay? Endothermic, it cools down because energy is absorbed to make the products because they're at a higher energy level. Exothermic, it heats up because energy is released to make when you make the products because they're at a lower energy level. So it's just vice versa. When you make flashcards, that will become really simple. Nice little diagram to help you with that. Now, a question that you could test yourself on at home. We don't have much time left, so I don't want to go through this now because I do want to make sure I've gone over the work for this week again. But the last thing we're going to do is talk about reversible reactions and equilibrium. So a reversible reaction is a reaction where I can make A and B react to form C and D, but I could also react C and D together to form A and B. So that means you can have a forward reaction, which is where it goes forwards along the reaction, so from left to right. But I can also have the reaction going backwards from C to D to A and B. Now, when we did this last time, I think I confused quite a few of you, and we got confused a little bit about, well, what examples do we have of this? Now, this video here, I'd really like you to watch, and I'm not just plugging my own videos here, well, I am a bit, But I went into school on Friday and I recorded a video of me doing a reaction, which is a reversible reaction. And I take you through it in a little bit more detail. So it's only like an 8-minute video. So I'd really like you to have a little watch of that. And it explains it in a lot more detail. Okay. And then hopefully you'll get a better understanding of it, because I actually go through this reaction here, which is when you heat hydrated copper sulfate, because it's an endothermic reaction, it needs to absorb energy to react. And you end up with anhydrous copper sulfate and you produce steam as well. I then can reintroduce water and push the reaction back the other way, which is an exothermic, so a little bit of energy is released, and make my hydrated copper sulfate again. Like I said, that video is on these slides, so will be on the slides when your teacher publishes them in the Google Classroom. It's also on the Science YouTube channel. Lastly, a keyword definition that we briefly went through, but we're going to go through in a lot more detail after half term, is what equilibrium is. So equilibrium is reached when the rate of the forward reaction, so A and B reacting to make C and D, is equal to the rate of the backward reaction. So C and B reacting together to make A and B. Now, in equilibrium, sometimes it can appear like not much is changing. And that's because they basically balance each other out, the forward and the backward reactions. Okay, now it happens in a closed system, and that means something with a lid on. And that's important because lots of exam questions will ask you about why this is able to reach equilibrium. Equilibrium, guys, is a balance. It's a fancy word for reaching some sort of balance. Okay, now that is the revision of the stuff we've gone through so far. Apologies. Now, what I've popped on this slide here are some support for you if you need it. So the webinars from the last 2 weeks, and the reversible reactions video I did for you on Friday. I've also added a video here about how to revise, because your work from this week is to do the self-assessment form in your Google Classroom. It's to have your individual class Zooms with your teachers to go through anything in specific detail that you need to, and then to go back and improve upon the task that you were given feedback for. So looking at your feedback, liaising with your teachers, what do I need to do? Those of you that have not submitted all your work, that is what you need to do, okay? It's a matter of going back and submitting things to catch up. Lastly, you need to look at some revision. And it's important to revise as you go. If you leave your revision all to the last minute, and at the end of C2, you're going to have a big mountain. So it's really useful to do little bits of revision as you go. I have got a how to revise video here, like I said, that the Year 11s have found really useful, that you can use to start your revision. And I have just done a video on how to make good flashcards that I will get uploaded in the next probably in the next hour. So we'll get that published to you as soon as possible. Now, this week is about reflecting, reviewing and revising. So there's nothing brand new as such, but it is about improving your work. Some of you will feel really confident and just go straight to revision. Some of you won't get to that point yet, and that's absolutely fine. Really important this week that you liaise with the staff around you. Now, that is the end of this webinar. If you have any questions, you may stay and we can go through them. But remember, you will have some individual Zooms with your teachers. If not, you are free to leave and to crack on with some work and to get ready for your next webinar if you've got something in a little bit. But thank you all for coming. It's really great to see so many of you coming repeatedly. And this video will be available on YouTube once I have finished and it has been uploaded too. So anyone who has any questions, please do ask them. Yes, Soren, we will go through evolution of the atmosphere. We haven't actually gone through it together in our webinar. So we're focusing on what we've done in our online learning, but we will get to evolution of the atmosphere, yes, later on. It's one of my favorite topics in chemistry, actually. Anything else from anyone else? If not, you are free to go and go about your day and do your work. It's really lovely to see you all. And in fact, what I'm going to do now is I'm going to have to end the webinar because I just don't want to be ended like I have been in previous weeks. Okay, thank you all for coming, and thank you, Mr. Bush, for your help. And I'll speak to you all very, very soon.